So let us do a simple example of the Navier-Stokes equation. This example is very complex, and that you would require information well beyond what we are providing in this course. But we are providing the basics for you to understand what's going on in this picture. So in our first example, they tell you that you have two infinitely long walls. So imagine, before we go in details, imagine that you have the two palms of your hands and you have a liquid film in between them. So you put oil in between them, and your bottom hand remains fixed while your top hand is actually moving over your bottom hand. So we're simulating this scenario by having a bottom wall and a top wall, and you have the oil in between them. That's the oil between your hands. Now you want to imagine that your hands are infinitely large. And the oil film is relatively thin, or actually is quite thin, for the assumptions in this problem to be valid. So we have the two walls separated by a distance 2h. Our coordinate system is y and x. X is along so the top wall is moving. That's your hand is being dragged on top of your bottom hand, and this is an exaggerated view. Your top hand is at a value of y equal h, and the bottom hand is at y equal minus h. Again, your hands are infinitely large, and in the limit that time goes to infinity after you start moving your hands on top of each other, or moving the top wall over the bottom wall, the flow will become steady. So we're making the assumption that we have a steady flow. We're making the assumption that the flow is two-dimensional. So we'll talk about this in a little bit more detail, and that the flow is fully developed in the x direction, which means that if I look at the flow velocity at x1 and the flow velocity at x2, I won't see that there is any difference in the flow profile. It'll be exactly similar between x1 and x2. So that's what we mean that it's fully developed, that there's velocity v does not vary with x. And in this particular example, they tell us that there is no applied pressure gradient there's no inlet and outlet, because this is an infinite system. There's no applied pressure gradient in the fluid. So the pressure is independent of x, and they tell us to neglect gravity. So let's talk about each one of those boundary conditions, or these assumptions, and see what it means, because they will repeat over and over again. So when we say we have a two-dimensional flow, as you have seen a few slides ago, it's two-dimensional in the x and y. So the missing coordinate is z. So our flow, our velocity, is independent of z. That's what we mean by two-dimensional flow. When we say steady, it's easy, that the velocity is independent of time, the velocity field, which is the small u, small v, and small w, the three components of velocity. And this is an important assumption. We're making the assumption that the flow only goes in the x direction. So it's unidirectional in the x, which means my vertical velocity v and the velocity into the page w are actually zero, and the only non-zero velocity is my u. So I don't have a v or w, I only have a u. So you see, we've made a lot of simplifications just by saying a unidirectional flow. And then we're making the assumption that our flow is fully developed, which means that the variation, so this should be x, not z, that's a typo. The variation in x of the quantity, which is the velocity of the flow, is zero. So this should be x. dv by dx is 0. And we're saying that there is no applied pressure gradient in the x, so dp dx is 0. So let's look at the Navier-Stokes equation now and see how we can use those assumptions that we started with. And we also are ignoring gravity. Let's see how these assumptions translate into simplifying the Navier-Stokes equation. We'll start with the continuity equation. And we'll start term by term. We can get rid of the v, so we can say that the dv dy and the dw dz are 0 just by saying that the flow is unidirectional, which tells us that du dx is 0, because if this is 0, but we can also say from the assumptions that we're given that du dx is 0 because it's fully developed. We can say dw dz is 0 because it's two-dimensional. dv dz is 0, which gives us that the dv dy is eventually 0. But you can, as we have said, you can start with the unidirectional, and it just gives you all three terms in the continuity equation to be identically equal to 0. Now let's look at term by term. du dx is 0 because it is because it's steady flow. U du dx, so we have a du dx, and that's a du dx. It's fully developed, so that cancels out. And then my flow is unidirectional, so my v is 0, so that cancels out. And also, because the flow is unidirectional, my w is 0. Or I can invoke the assumption of two-dimensionality. dv dz is 0. So either the w is 0 or that is 0, and both of them are actually 0. They tell us to ignore gravity, as we said in the previous slide. No applied pressure gradient in the x direction, so dp dx is 0. And let's see, how about the del square u by dx square? So it's the partial by partial x of du dx. And here we have du dx to be 0 because it's fully developed, so that goes away. D del square u by dy square. We don't really know much about this. None of the assumptions that we have started with gives us the right or allows us to get rid of this term. But we know that we can get rid of this term, the partial by partial z, because we are a two-dimensional flow, as we have seen here. So this equation simplifies very well to del square u by dy square multiplied by viscosity over density to be equal to 0. Let's look at, and this is the x momentum of the Navier-Stokes equation. And our flow is unidirectional in the x direction, and that's why we'd expect to see a variation in the velocity here. Let's look at the y momentum of the Navier-Stokes equation. Because my flow is unidirectional, everything with a v will just cancel out. This is very easy. Everything has a v in this equation. V, v, and v. Same thing, and there's no gravity. Same thing with the z momentum equation. So all these cancel out. So the y momentum and z momentum just tell me that the pressure is independent of y because dp dy is 0, and the pressure is independent of z because dp dz is 0. So let's clean this up. Let's move on to a new slide. Continuity, three Navier-Stokes equations. That's what they boil down to. This is the x equation, and because mu over rho, we divide by it because the right hand side is 0, so we end up del square u by dy square is 0. So let's deal with this. We can integrate once, so I get du dy is constant, and we're integrating both sides. Integrate. So now separate variables. So you take the dy to the right hand side. So you integrate the du relative. So when you integrate du, you're going to get u, and when you integrate constant times dy, you're going to get a constant times y, and then you get, because we integrate again, we get a new constant c2. So our solution, because the question, so let me step back, the question was to actually find the velocity distribution of the fluid between our two walls, between our the palms of our hands. What does the velocity profile of the oil film look like? What does the velocity distribution look like when one hand is sitting stationary and the other hand is moving on top of it and shearing the oil, and assuming that our hands are infinitely large? We look at the y momentum equation. As we said, dp dy is 0, so p is independent of y, so we don't see y here. And same thing, p is independent of z, so we don't see. But since p is only a function of x and y here, and here it's only a function of x and z, so p wouldn't depend on z, and p wouldn't depend on y. And we already know that p, from the previous slide, p is independent of x, so in fact p is independent of x either. So my p actually is just a constant. P of x, y, and z is a constant. It's independent of x, y, or z. So now we have pretty much solved our Navier-Stokes equation, and the solution, as we said earlier, would be to know the pressure and the velocity in the domain. However, we have those constants of integration that we really need to figure out. So we're after finding the velocity distribution. We know now that the velocity distribution is linear. So we need to apply the boundary conditions to get C1 and C2. So at the top boundary, we have no slip. So at the wall here, we're now talking at the velocity of the fluid would have the same velocity of the solid boundary. Since the solid boundary is moving at velocity v, then the velocity of my fluid at y equal to plus h here is going to be the same velocity of the wall. It's v. And if I now take the bottom boundary, y equal minus h, another typo, that's minus h. I also have no slip because it's a solid boundary, but my wall is fixed. It's not moving as the top wall. So I get a velocity of 0. Right, so so let's plug those back into the equation that we started with before. This is our C1 and C2. So we'll take U at plus H equal V. So plug here H, because that's the H. You plug it here. So Y equal plus H, C1 plus C1H plus C2 is equal to capital V. And that's what we get over here. Capital V is C1H plus C2, and then you plug in the second boundary conditions into the equation. So minus H goes into everywhere there's a Y. There's a minus H here, minus H, and that's equal to 0. So 0 is equal to minus C1H plus C2. So now I have two equations with the unknowns being C1 and C2, so it's a linear system of equations. We can sum them up, so add them up, and you get C2 to be equal V over 2. So how do we add them up? V plus 0 gives me V, and C1H minus C1H gives me 0, and C2 plus C2 gives me 2C2. And then if you subtract them, V minus 0 gives me V, C1H minus C1H gives me 2C1H, and the C2 will cancel with the C2. So I get C1 and C2. Take C1 and C2 and plug them back into the equation that we started with. So for C1, plug in V over 2H, and for C2, plug V over 2. So that's what you get. That's your... Now we have completely described the velocity. We have now completely found what the velocity distribution inside inside the oil film between your hands looks like. It is linear. And we can double check that our solution. So the first step is to actually double check that our solution is correct. We didn't make a mistake along the way. And how do we double check our solution? Is by the solution should satisfy the boundary condition. So let's plug in y equal minus h. So here's minus h. Minus h over minus h is over plus h is minus 1, plus 1 is 0. So I get a 0 velocity at the bottom wall at minus h. Great, so that checks. Let me plug in y equal to plus h, and I get y at u at h gives me v over 2, h over h is 1, plus 1 is 2, the 2 goes with the 2, so I get v, which is the velocity of the top wall. So that also checks. So it looks like my solution actually satisfies the boundary condition. So it doesn't seem that I have made any obvious mistake along the way in finding my solution. So this is how it looks like. You'll see that because of the no-slip condition, this is the velocity profile. So if I take this section and look at the velocity of the fluid particle at each one of those points along this line, we have the slowest velocity at the bottom wall because it's stationary, and the highest velocity. So this is u of y is the velocity of the oil film between the two plates, between your two hands that you're rubbing. Now, what can we do with this type of information? We can do a lot. So now we have really solved. We have now obtained everything that we need to know about this flow, and from here on we can go do engineering analysis. This was the math part of our study, but next we can go do the really engineering stuff, and the real engineering stuff is we want to know how much mass flow rate is going through, is being carried or is being dragged by the top wall and the oil film, because we see that the oil is moving, so mass is being dragged. And then the other thing we might want to know is how much friction am I generating on my bottom wall, how much friction am I generating on my top wall, or how much friction is there at the center line of the flow. So these are all valid questions. So let's try to give them an answer. Let's compute the mass flow rate, as well as let's find the friction force per unit area on here they ask us about on the bottom wall. So we have the velocity profile, mass flow rate. If I want to know what the mass flow rate is, I need to know which area we're looking at. We're looking at the area between the two plates. If my width into the page is b, so that's my b, then I would take an elemental area dA over here, and that dA is equal to dy times the width into the page b, and the velocity perpendicular to it is actually the u. So my dm dot, my mass flow rate, is the integral of dm dot. It's just the density of the flow multiplied by the velocity by the area dA, which is b times dy. And you integrate from the bottom wall to the top wall, from y equal minus h to plus h, and you end up, when you do the integration, to have the mass flow rate to be equal to 2h times b. What is 2h times b? 2h, this is h and this is minus h, so this is 2h. When you multiply it by b, the width, that's an area. So here you get an area multiplied by density, and this is the v over 2. What do you expect this v over 2 to be? You have v is 0, or u is 0, and u is capital V. So I have a line, so that v over 2 is actually the average velocity over the whole line, so it's the u average. And that's how we define the average velocity. That's how we actually can find the average velocity, is we find the mass flow rate and divide it by the rho a. So that gives me the average velocity over this whole section. So this would be more like a one-dimensional flow. The velocity is independent of y. It looks like this. That's the v over 2 would be described by this profile, while the pink profile is described by the equation we achieved in the previous slide. So that's our average flow velocity. And going back to the slide on, let's just erase some of those items here. Let's go back to the slide on shear stresses. I'm not going to go back here, but I would like you now to, but if you go back, if you pause and go back, you will see that shear stress is the friction. So when they ask us to look at the frictional force per unit area on the bottom wall, the force, there are two forces that a fluid can exert on an area. One is shear stress, and the other is pressure. And we found in the previous slide that the pressure is uniform. So if they ask us to find the normal force, they wouldn't ask us for the friction. But here they're asking us for the friction, so they're hinting that we should look at the shear stress. And the shear stress, so the frictional force is just the shear stress on the bottom wall. So tau, so the force that I have drawn here, the direction of this force, it is the force of the wall on the fluid. But they ask us to find the friction force per unit area on the wall itself. So let's just erase that. It will be in the opposite direction. To find the force, that's my WhatsApp, I think. To find the force of the fluid on the wall, that's how the fluid is shearing the bottom wall. That's F friction. And that frictional force is equal to the shear stress multiplied by the area of the wall. What area of the wall are we talking about? It's the area parallel. So it is this x distance multiplied by the width into the page, b. So x times b. And that's what you get over here. And if you want to be very critical, we're talking about the tau yx. The tau in the x direction, on, because this is the y, this is the surface perpendicular to the y coordinate, so that's why it's tau y, and it's in the x direction, is the direction of the force, or the direction of motion. So friction is always in the same along the direction of motion in the opposite, along the line of motion in the opposite direction. And tau, in a few slides ago, we looked at it at the 6 terms of tau, and we are only interested in one of them now, because tau yx, you go back, you'll find it's partial u by partial y, and you go here, you do partial u by partial y, you derive of u of y, right? You do partial u by partial y. That's your y, so you'll get v over 2h, and when you derive constant, it's going to give you 0. So you're going to get v over 2 times h. So that's the du dy, and multiplied by viscosity, so that's what you're going to get. We need to erase that. Right, so you get viscosity times the derivative we found here, v over 2h, times the area, which is the width into the page, times the x. And if I want the force, frictional force per unit area, I divide by the area, which is b times x, and you divide by b times x. So the force per unit area is the viscosity times the velocity divided by 2h. All right, I hope this makes sense. Now let's move on to a similar problem. In this problem, we're still talking about 2 plates, a top plate and a bottom plate, but in this case, both of them are fixed. So we're not rubbing our fingers against each other, but imagine now that you have those 2 plates and you're blowing from one direction, so you're supplying a pressure, and the other, so here you have a high pressure, and at the other end you have a negative pressure. So we're supplying a pressure gradient for this particular example. So this is a pressure-driven flow. The previous example right here is called a shear-driven flow. Yeah, a shear-driven flow. And what we have here is a pressure-driven flow. So these are two different mechanisms for creating motion in a fluid, either by applying a pressure force, like here in this particular example, or by shearing the fluid as we had in the previous example. So we have a very similar geometry, y equal plus h minus h, x and y are in the directions that we had. The walls are infinitely long. Both of them are fixed. None of them are moving. We have a two-dimensional flow in the x direction, and our flow is steady. So as our plates, as we apply the pressure gradient for an infinitely long time, we get to a steady state, and that's what we're trying to study. And we're making the assumption also that in the limit that my flow becomes steady, it will also be fully developed. That means the flow profile right here will be the same as the flow profile at a different x. So the flow becomes independent of x. The one thing that we have different here in this problem is that we said there was no applied pressure gradient in the previous problem. Here we're saying we have a constant applied pressure gradient. So we'll just redo this problem, the previous problem, and use a dpdx is constant rather than 0. And as we said earlier, we're ignoring gravity. So you go back, it's the same Navier-Stokes equation, you simplify them, and you're going to end up for the x momentum, just like we have done, go back to the previous video and plug in dpdx to be constant. We're going to get the same equation for the x momentum, except we had it to be equal 0 in the previous slides. Here we have it to be equal to the pressure gradient. And then you integrate once, and then you integrate again. So here's where you really would like to go back to your previous slide. If this is too fast for you, play that again. So when you integrate once and twice, you're going to get the first constant of integration and the second constant of integration. And now we need to apply our boundary conditions. But before we apply our boundary conditions, if you go and look at the y and z momentum, that you're going to get information about the pressure to be independent of y or z. dpdz and dpdy is equal to 0. So the pressure is only a function of x, as we have drawn it over here, as it is given in the problem statement that dpdx is a constant. So p of x is given to be linear. That's why dpdx is constant. So this is p at the in, and this is p at the out. Or if this is an infinitely long plate, which it is, two infinitely long plates, then that's what the pressure gradient looks like. It has a certain slope of constant c. So the constant is the slope of this pressure gradient. So you integrate once, integrate twice, just like we had before. And now we have this, we have C1 and C2, and we now have a second order equation. It's not linear anymore. So to get, so yeah, right. So here we also have the y and z components of the equation of the Navier-Stokes equation. So the pressure tells me that P is only a function of x and z in the y direction, and the z component tells me that the pressure is only a function of x and y. But since this guy and this guy are the same, I have x in both of them, so it has to be function of x. But I only have, here it tells me, this equation tells me that the pressure is not a function of z. And this equation, it tells me it's not a function of y. So then, because they're the same pressure, we get rid of the z and we get rid of the y. They only tell me that this is a function of x, which is what we knew all along, is that the pressure is linear in x, and that's the equation that is provided over here to be linear. So we didn't really discover anything new. So the next step is to find C1 and C2, our constants of integration. So now it's an old story. We apply the boundary conditions at y equal h and minus h. Both of them are stationary. Top wall stationary, bottom wall stationary. Top boundary no slip, and the bottom boundary is a no slip. So we get C1 equal, so try and get, so please pause this video here and make sure and try and do this on paper and double check that we didn't make a mistake here. Double check our answer and see that C1 and C2 are actually what is written on your screen. But assuming that they are correct, we found C1 and C2, we plug them back into the equation. That's C1 and that's C2. And now we find the velocity distribution. And let's talk about this. And if we try and simplify it, we'll take the dpdx is constant, the h is constant, and the viscosity is also a constant. So we'll take it as a common denominator, and I take a minus dpdx. So we know that the pressure is, the dpdx is negative. So this is my minus dpdx. That's a positive term. And this number is always positive or is less than 1 all the time, except at y equal h. So that's my u of y, and that's a pressure-driven flow, as we said. Pressure-driven flows have this property that they are parabolic in y, and this is what it looks like. The plate is infinitely long into the page of width b. That's what it means to have a two-dimensional flow. It's independent of z. So wherever you are along the width b, you're going to get the same profile that you get over here. And this, so I would like you now to do the same exercise that we have done before. I would like you to find the mass flow rate that's going between the two plates in this pressure-driven flow. Find the average velocity, and also what is the shear stress on the bottom wall, tau, the friction per unit area, tau on the bottom wall as well as on the top wall. You can see from symmetry that they're going to be equal, whether tau bottom and tau top. So let's find those. So I'll leave that to you to do. And now we'll solve, because it's a good exercise. Now we'll solve a third problem. And in the third problem, we're making the assumption that the top wall is moving, and I'm also having, and the bottom wall is stationary, but I also have a constant applied pressure gradient. So the assumptions that we have in the previous two examples, we are putting them all together in this example. And if you look at our equation of motion, it's actually going, it's so here, let's look at that. Let me just erase this guy here. All right. Let's look at the equation of motion. It's a partial differential equation. Is it first order or second order? It is second order. And is it linear or nonlinear? That's a constant. So it's a linear partial differential equation. And that thing is a constant too. So if you have a linear partial differential equation and you find solution A, which is this guy, and you find solution B, which is this guy, then we can implement the superposition principle, which says that if solution A satisfies my governing equation and solution B satisfies my governing equation, then the sum of the two solutions actually satisfies my governing equation. So all you need to do is just go back, sum the linear profile to the parabolic profile, and we don't really have to solve for it again. So that's a beautiful property of linear equations. And why we used all those assumptions is because one, it's easier to solve linear equations, linear partial differential equations, but also we can apply the superposition principle too. And this is a partial differential equation property. And that's about it for Cartesian coordinates. What we are going to do in the next lecture is to actually go over solutions of the Navier-Stokes equation in cylindrical coordinates, because we are particularly interested in the flow in a pipe. Because you see those everywhere. If you go now to your kitchen or to your bathroom, you'll see that your tap, the pipes behind the wall are all round pipes, and it's a canonical problem that spans all types of engineering applications. So it makes sense for us to look at the solution of the Navier-Stokes equation in cylindrical coordinates. But we have derived the Navier-Stokes equation in Cartesian coordinates. We're not going to spend our time deriving it in cylindrical coordinates. What you really need to do is jump to your Appendix D, and it gives you the Navier-Stokes equation in cylindrical coordinates. Albeit it's a little bit not straightforward, because they give you the Laplacian operator here and the convective time derivative. So they give you the continuity right away, but then your R, theta, and Z momentum equations are given in terms of the convective derivative and the Laplacian for the shear stress. So you'll see the Laplacian on the right-hand side, while the convective derivative, you'll see it on the left-hand side. Here, that's the convective derivative, and that's your Laplacian. And all you need to do is just apply. So here it's shorthand notation. We're not going to be dealing with the energy equation, which is great, or the angular velocity components. We're only interested in the continuity equation and linear momentum conservation. So next time we are going to talk about the Navier-Stokes equation in cylindrical coordinates. We're going to spell them out, and we are going to implement them for a pipe flow, pressure-driven pipe flow. So thank you guys for listening, and I will see you next time. And goodbye.